So in lesson 2 we're going to be looking at isotopes. So isotopes are variations of atoms of an element. So in terms of the three subatomic particles, it's the number of protons that defines that atom as being the element that it is. So for example, carbon. Carbon has 6 protons. So any atom, no matter how many electrons or how many neutrons it might have, as long as it's got 6 protons, it will be an atom of carbon. Let's take an atom that contains 2 protons. That will always be helium. It doesn't matter how many neutrons or electrons it has. If it has 2 protons, it is helium. So the number of protons fundamentally defines the atom as that particular element. So with isotopes, what's really important is they are atoms of the same element. So they must have the same number of protons. But what has changed is they have a different number of neutrons. So if we have a quick look at this table, so we should be able to fill this in really quickly from last lesson. So we should know that protons have a relative mass of 1, neutrons have a relative mass of 1, and electrons have a relative mass of 1 over 2000. So they're 2000 times lighter than a proton. And their relative charge, a proton has a relative charge of +1, a neutron has no charge, and an electron is -1. So, as I just said before, so an isotope is an atom of an element with the same number of protons but a different number of neutrons. Okay, so that's really important. Same number of protons, different number of neutrons. So let's look at the effect that's going to have. Well, isotopes are still atoms, and atoms have no charge overall. So if we were talking about isotopes of carbon, for example, so carbon atoms all have 6 protons, which means they also have 6 electrons. So the number of electrons, the number of protons does not change. The only thing that's changing is the number of neutrons. So because the neutrons have no charge, they have no effect on the charge of the atom. So isotopes don't have any variation in charge, but they do have mass. So if you had less neutrons in the nucleus, then your atom would be lighter, and if you had more neutrons in the nucleus, then your atom would be heavier, and that does have an effect on some of its physical properties. So some of the questions you're very commonly going to be asked are, why do isotopes have identical chemical properties? And that's because the chemical properties are determined by the electrons. And because we've got the same number of protons and same number of electrons, there's no difference in their chemical properties. So chemical properties are determined by the electrons, and isotopes have the exact same electronic configuration. Now, we've not come across this term yet, but it is the subject of the next lesson. All you need to know at this point, when we say electronic configuration, we're talking about the number of electrons, and we're talking about where those electrons are found. So you don't need to know any more details at the moment, just that they're identical. The number of electrons that the different isotopes have and where those electrons are in terms of shells is identical. And if the electrons are identical, then their chemical properties are going to be identical. However, they will have different physical properties, and that is due to atoms having different masses. Because neutrons have a relative mass of 1. So these isotopes are going to have different masses, because let's take carbon-12 for example. Carbon-12 has 6 protons, 6 neutrons. But carbon-13, it's still carbon, so it still has 6 protons, but now it has 7 neutrons. So an atom of carbon-13 is going to weigh 1 more. And because of that, you get some changes in their physical properties. So there are 3 changes you need to be aware of in terms of physical properties. Their mass changes, and because their mass changes, their density changes, and so therefore does their melting and boiling points. Those are the 3 physical properties that change between isotopes. Now remember, their chemical properties are identical, so the way they react, how reactive they are, the compounds that they form, the other elements they react with is identical. Their structure and bonding, identical. It's only these 3 physical properties that change. So what I'd like you to do is, using the periodic table, identify what the mass number is, the atomic number of these different isotopes, determine the number of protons, the number of neutrons, the number of electrons. Okay, so what we should see here is we've got the chemical symbol and 2 numbers. Remember, the big number is the mass number and the small number is the atomic number. So our mass number here is 12, our atomic number here is 6. Here it is 13, 6, 1, 1, 2, 1, 35, 17, 37, 17. Now, first thing we should notice is I've got 2 isotopes of carbon, 2 isotopes of hydrogen, 2 isotopes of chlorine. Notice that the atomic number is the same. So both isotopes of carbon have the atomic number 6. Both isotopes of hydrogen have the atomic number 1, and both isotopes of chlorine have the atomic number of 17, because that is telling us that the carbon atoms have 6 protons. So even though they're isotopes, they are still carbon, so they must have 6 protons. 2 isotopes of hydrogen, but they are both hydrogen, so they must have 1 proton. 2 different isotopes of chlorine, but they are both chlorine, so they must have 17 protons. Now, these 2 carbon isotopes are going to have identical chemical properties because they've got the exact same electronic configuration. And these 2 hydrogen isotopes are the same, identical electronic configuration, identical chemical properties, and the same for the chlorines. So they're going to have the same structure and bonding, they're going to have the same reactivity, they're going to have the same products that they form when they react with other elements. What's going to change, however, is the mass, the density, and the melting and boiling points. So if we look at their protons, so their atomic number tells us the number of protons. So both carbons isotopes have 6 protons, both hydrogen isotopes have 1 proton, and both chlorine isotopes have 17 protons. It's the number of neutrons that is going to vary. So for carbon-12, 12 minus 6 is 6. For carbon-13, 13 minus 6 is 7. So it has 1 more proton, which means its mass is higher. 1 minus 1 is 0, so hydrogen actually has no neutrons whatsoever, but this isotope, also known as deuterium, has 1 neutron. 35 minus 17 gives us 18, and 37 minus 17 gives us 20. So that chlorine 37 has 2 more neutrons than the chlorine 35. The number of electrons, however, does not change. So if you've got 6 protons, you get 6 electrons. If you've got 1 proton, you've got 1 electron. If you've got 17 protons, you've got 17 protons. So it is only the number of neutrons that changes. And because the electrons are exactly the same, you have the exact same chemical properties. Because the protons are the same, they are the same element, and it is the variation in the number of neutrons, 6 or 7 or 0 or 1 or 18 and 20, is going to cause these isotopes to have a variation in their physical properties, but identical chemical properties. So when we were looking at the periodic table before, we identified that the large number is the mass number. Okay, so the definition for the mass number was the number of protons plus the number of neutrons. Now, we know that protons have a mass of 1 and neutrons have a mass of 1. So our mass number can only ever be a whole number because you can't have half a proton or half a neutron. So if that's true, if our protons have a mass of 1 and our neutrons have a mass of 1, then our mass number has to be a whole number. Yet you look at the periodic table and you will find some of the elements have decimal values. That's because the value actually shown on the periodic table is not the mass number. Now, the periodic table you're going to use at Key Stage 3 and even at GCSE is predominantly going to be whole number values, but chlorine is a good example. So chlorine shows up as 35.5. Now, there is not a single atom of chlorine that has a mass of 35.5. So why does the periodic table show the mass number as being 35.5? And that's because in the periodic table, what is shown here is not actually the mass number. It's the relative atomic mass. And the reason why it's a decimal value is because of the isotopes. So relative atomic mass, which is what is actually being shown, rather than the mass number, is an average, and it's an average of all of the isotopes of that element. And it's not normally a problem because isotopes are quite rare. So if we're looking at carbon, so if you look at the periodic table, carbon has a relative mass of 12. The mass number of carbon is also 12. So why isn't this a decimal? Well, because yes, there are other isotopes of carbon. There's carbon 13, there's carbon 14, there's even carbon 15. But they exist in such tiny, tiny percentages that it doesn't change the overall value on average. There's lots of isotopes of hydrogen as well. You have hydrogen, deuterium, and tritium, so hydrogen 1, hydrogen 2, hydrogen 3. And again, the hydrogen 2 and hydrogen 3 exist in such tiny amounts that on average they don't affect the value. So why is chlorine affected? Well, chlorine is affected because it has 2 isotopes, but there's actually quite a large abundance of both. So the average isn't going to be a whole number. So our relative atomic mass, which is the value that's actually shown on the periodic table, is an average. So it is the average mass of all isotopes of an element compared to carbon 12, and we use carbon 12 as sort of our reference point. So the point is here that our relative atomic mass is the average of all the isotopes, and it's not normally a problem because all of the isotopes of elements are usually very, very tiny percentages. But with chlorine, there's a much larger percentage of the isotopes, which leads to us getting this decimal value. So you might be asked to calculate the relative mass of an element, and you'll have to be given 2 bits of information. You have to know the mass number of the individual isotopes, and you need to know the abundance of each isotope, so how much of that isotope is there. Usually the abundance will be a percentage. So the formula is simple. In order to calculate the relative atomic mass, you need to times the mass of the isotope, so the mass number of the isotope, by its abundance. And then you add the sum of the the mass of the next isotope times by its abundance. And you just keep doing that until you run out of isotopes, and then you divide it by the total abundance. Now that doesn't make a huge amount of sense on its own, but if we use an example, it should make more sense. So I'm going to stick with chlorine. So chlorine has two isotopes, chlorine 35, chlorine 37. So these are the mass numbers. So the chlorine 35 has a mass of 35, and the chlorine 37 has a mass of 37. And it says that the chlorine 35 is 75% abundant, and the chlorine 37 is 25% abundant. So all you have to type in, you can use a calculator for this. So the mass of the first isotope, so chlorine 35, so it's going to be 35, and its abundance is 75%. So you do 35 times 75%. Plus the next isotope, which is chlorine 37, which has a 25% abundance. So we're going to do 37 times 25 over the total abundance, which 75 and 25 is 100. And that's where the 35.5 comes from that we see in the periodic table. So it is the mass of isotope 1 times by the abundance of isotope 1 plus the mass of isotope 2 times by the abundance of isotope 2 over the total abundance, which will usually be 100%. Now if you had 3 isotopes, you would just add another bracket here, and you'd just do the mass of the third isotope times by the abundance of that third isotope. So here we have some examples where we've been given an element and we need to work out its relative mass. And we've been told the isotopes that exist for that element and the abundance of those isotopes. So I'm going to go through 2 of these, and then the rest you can complete yourselves. So I'm going to do the copper and the magnesium, because I just wanted to show you how it changes if you have more than 2 isotopes. So we'll start with the copper. So you need to identify the mass numbers of your isotopes. So we've got copper 63 and copper 65, and their abundances, which are here given as percentages. So the first isotope is copper 63, so I'm going to do 63 times by its abundance, which is 69.2, plus the mass of the second isotope, which is 65 times by its abundance, which is 30.8, over the total abundance, which if you add those together is equal to 100. And then I'm just going to grab my calculator quickly and type in 63 times 69.2 plus 65 times 30.8 over 100, which is equal to 63.6. And there's our answer. And we can tell that that's reasonable because your number has to be roughly in between the 2 masses of the isotopes. We know that we had copper 63 and we know that we had copper 65, so our answer had to be between 63 and 65. It couldn't be bigger than 65 and it couldn't be smaller than 63. And also you'll notice that it isn't just going to be 64. It isn't going to be bang in the middle, because there's more of the copper 63 than there is of the copper 65. So by looking at the percentages, you could have worked out that my answer had to be between 63 and 65, and because there was more of the copper 63, it was actually probably going to be closer to 63 than it was 65. So the magnesium example, this time we've got 3 isotopes, but it doesn't change what we're going to do. You identify the relative masses, so 24, 25, 26. We can see their abundances right here, and we're just going to do the same thing. We're just going to add a third bracket onto this equation. So the first one's going to be 24 times 79 plus 25 times by 10 plus 26 times by 11. And again, 79 plus 10 plus 11 is 100. And I'm just going to type that into my calculator now quickly. So 24 times by 79 plus 25 times 10 plus 26 times 11 over 100, 24.3. And again, I'm looking at my masses of my isotopes. I've got 24, 25, 26, so it can't be lower than 24 and it can't be higher than 26, so 24.3 seems reasonable. And also look at the abundance. There's 80% of it is magnesium 24, so it makes sense that my answer is closest to being 24. So I want you to have a go at the remaining questions. So we've got lithium and bromine, iron and krypton, and that should take you no longer than 10 minutes. So I'm just going to go through the answers quickly, and again, mark your own work, self-assess, and make any corrections you need to in green. So for the lithium, we've got the relative mass of the first isotope is 6, and its abundance is 7.6 plus 7 times by 92.4 over 100. And again, I can see my answer has to be between 6 and 7. There's a significantly higher proportion of lithium 7, so my answer is going to be much, much closer to 7 than it is 6. So 6 times 7.6 plus 7 times 92.4 over 100 is 6.9. So for the bromine, mass number is 79 times by its abundance, which is 50.7, plus bromine 81, which has an abundance of 49.3 over 100. So 79 times 50.7 plus 81 times 49.3 over 100. And again, we can see my answer needs to be between 79 and 81, and there's roughly 50-50 abundance, so you should be predicting that this one's going to come out very, very close to in the middle, and it actually does. If you round it, it comes out as 80 or 79.986, but that rounds to 80. So iron has 4 isotopes. So we're just going to exact same formula. We're just going to have to add another bracket for that 4th isotope. So we've got 54 times by 5.8. We've got 56 times by 91.8. We've got 57 times by 2.1. And we've got 58 times by 0.3. All over 100. So if I type that in, so 54 times by 5.8 plus 56 times 91.8 plus 57 times 2.1 plus 58 times 0.3 all over 100. And again, we can see from the abundances that it's going to be much, much closer to 56 than any of the others, because it's at 91.8 8% abundance. So that rounds actually, again, it rounds to 56. And the last one then is krypton. Now we've actually got 6 isotopes here. I'm going to struggle to fit this on, but it's the exact same thing. You're just going to have 6 sets of brackets across the top. So we've got 78 times by 0.4. We've got 80 times by 2.3. We've got 82 times by 11.6. We've got 83 times by 11.5. We've got 84 times by 57. And we've got 85 times by 17.3. Ooh, just about squeeze that on there. All of that over 100. Type all of that in. So 78 times by 0.4 plus 80 times by 2.3 plus 82 times 11.6 plus 83 times by 11.5 plus 84 times 57 plus 85 times 17.3, all over 100. And again, we know our answer needs to be between 78 and 85, and it is probably going to be closest to 84 because that's the most abundant isotope, and our answer actually comes out as 83.8, which is as we were expecting. And again, just like in lesson 1, we have a 10-question fact test. This is a mixture of questions from lesson 1 and lesson 2. So you have 10 minutes to answer all of these. So I'm just going to run through the answers. Again, you should be self-assessing your work and making any corrections that you need to in green pen. So what name is given to a substance that contains more than one type of atom or compound not chemically bonded? That is a mixture. What is the relative mass of a neutron? So they have a relative mass of 1. What name is given to a substance made of more than one atom covalently bonded together? Now, this covalently bonded, now you've not covered that yet, but this means it's a molecule. But I will accept compound. Why is the number of electrons the same as the number of protons in the atom? They are oppositely charged. Therefore, they cancel each other out, which is why the atom has no charge overall. What name is given to a substance that contains more than one type of atom chemically bonded? So this is a compound, so actually it's a 2 for 1, that question, because if you got this one right, you probably got this one the same. What does the mass number of an atom represent? It is the number of protons plus the number of neutrons. How many protons are in an isotope of chlorine-37? Now you just need to remember that it doesn't matter that it's an isotope, it's still chlorine, and chlorine has 17 protons. How many neutrons are in an isotope of carbon-14? So again, to get the number of neutrons, it is the mass number minus the atomic number. We know that the mass number is 14, and the atomic number of carbon is always 6. So 14 minus 6 is going to give us 8. What does the atomic number of an atom represent? It is the number of protons. And in the gold foil experiment, what was proven by the majority of the alpha particles traveling straight through the atom? It proved that the atom was mainly empty space. Okay, so correct what you need to correct in green pen and give yourself a score out of 10.